Thank you. So good afternoon, everybody. And so my name is Sylvain Hallé. I'm from University of Quebec in Chicoutimi in Canada. And before I start, I would like to thank the editors for allowing me to contribute to this book chapter. It's really appreciated, and it's a pleasure to be here with you. So the title of this chapter is A Stream-Based Approach to Intrusion Detection. And I'll start by saying something that we all already know now. So when you have a system, you can observe its behavior and record what the system is doing, whatever information system we're talking about, through a log of events. So the events, depending on the system, can represent many different things. And so the expected behavior of the system can be evaluated somehow by looking at this sequence of events that is produced by the execution of the system. And then you evaluate conditions on these events that are recorded. So I gave lots of examples of events that can be produced by various kinds of information systems. But of course, you can translate that to whatever field of application you're interested in. Now, what is a stream? Well, it's simply an ordered sequence of events of a given type. And then formally, we can define what is a stream processing calculation. It is basically just a function that takes multiple streams of events as its inputs and produces one or more streams of other events as its output. So it's a very generic definition. In this chapter, we're interested in attack or intrusion or anomaly detection. So in a very broad way, we could define this process as making the difference between two situations. On one side, situations that are expected, things that we call normal or routine or nominal. And on the other side, we want to identify situations that are somehow surprising or out of the ordinary, different, or just not okay. That's a very generic definition. Um, there are many approaches to this problem, and there's a taxonomy of existing approaches that classify these attack or intrusion detection systems into three broad categories. The first one is what we call anomaly-based approaches, which attempt to detect uncommon events or outliers in a set of data. Then there's multi-agent based approaches where you have cooperating units that observe and interact with an environment. And the third family is called knowledge-based approaches, where this time you have information that you know in advance about the expected behavior of the system. And then what you do is somehow compare the observation of the execution of the system with this information to decide whether the system is behaving normally or not. So in this paper, we are interested in this third category. So we will consider knowledge-based approaches, and in particular, what we call pattern-based approaches, where the abnormal execution of a system is represented in the form of patterns of events. And so if you observe an occurrence of this pattern of events, then you conclude that there is an intrusion, or there's an attack, or there's at least something that needs to be looked on in the execution of the system. Now, regardless of the technique that we use to detect these anomalies or these intrusions, there's a common issue is that they generate a high volume of alarms and related information. And so one of the main concerns in using these approaches is to try to reduce this volume. And there are two possible ways to reduce the volume. The first is to decrease the false positive rate because many times it's preferable to have more warnings than not so that you don't miss anything relevant. But of course, you pay a price for that. You have false positives. So you have warnings that do not represent an actual event that needs to be examined. So one of the possibilities to reduce the volume of information is to try to be as precise as possible to make sure that you generate as few false positives as you can. But there's also another way to reduce volume according to a different dimension, which is to try to reduce the amount of information that you provide in each occurrence of a warning, an alarm, or an anomaly that you potentially detect. And in this chapter, this is what we are interested in. So there are many works that attempt to decrease the false positive rate, but there are fewer works that address this second dimension where you reduce the amount of information that you provide regarding each potential incident. So the approach we propose is to view the problem of intrusion or attack detection as a form of runtime verification. Runtime verification is a subfield of software engineering, software testing in particular. And the way it works is that you have a system, whatever that system may be, and then you have some instrumentation that records elements of information about the execution of the system. So this instrumentation produces a trace or a log made of individual events, and then you have a monitor that evaluates in real time this flow of events that is produced by the instrumentation. What's interesting in runtime verification is that what the monitor does on this stream of events is to evaluate a formal specification. So it's a description of the expected content of the flow of events that is observed, but expressed in a formal or mathematical notation. So more precisely, the monitor is a process that updates a three-valued verdict. So it returns true if the input stream contains the pattern that is to be observed. It returns false if the stream can never contain the pattern, and it returns this unknown value otherwise. And you have an example at the bottom of the slide. If the simple pattern I want to observe is I see an A eventually followed by a B and eventually followed by a C, you see that as the stream of events is produced, the monitor produces a verdict that gets updated, and in this case becomes true as soon as the sequence of events that we are looking for has been observed in the stream. There are a few shortcomings, though, to the use of monitors for this particular purpose to detect patterns. The first one is that a monitor stops at the first occurrence of the pattern. So it's not made to detect multiple instances of a pattern, which, of course, in the case of a long-running process, is not something really desirable because there might be multiple occurrences of an attack over time. And so if the monitor has to be restarted every time it detects one, it's not very ideal. The other problem is that you have limited feedback because when the monitor stops by saying, I found something, all you have for as information to look into the pattern is the location of the last element of the pattern, and potentially everything that precedes is relevant to the occurrence of the pattern. The monitor does not give you any more information than that. So we're trying to address these two issues. And the solution we propose is just to run one instance of the monitor on every suffix of the input. So in the example that I've shown you just before, this would mean that I would run one instance of the monitor that starts at the first event, and you see the sequence of verdicts that it would produce. And then I would start a new instance of the monitor that would start reading the stream at the second event. And I would repeat the process for every new event that comes in. You would see here the sequence of verdicts that each of these monitor instances produces. There's, of course, an issue with this. First of all, running one instance of monitor per event is extremely wasteful. But it's wasteful in terms of resources, but it's also wasteful in terms of the information that you get. Because as you can see in the slide here, what you obtain are multiple matches for what is essentially the same pattern multiple times. So what we want to do is to try to come up with pruning tactics that would allow us to discard information from some of these monitors or some of the events processed by these monitors in order to reduce the volume, as I said in the beginning. If we have access to the monitor's internal state, we can indeed define what I call here pruning tactics. So here, the state of the monitor is very easy. It can be represented as a finite state machine that you see on the slide. So you remain in the initial state until you read the first A, then you remain in the green state until you read the B that you are looking for, and so on until you end up in the red state, which corresponds to a match of the pattern. So the first pruning tactic that we define is simply to discard monitors that remain in their initial state after consuming the first event. So you have an example here on the slide where you have the first monitor instance with the sequence of verdicts that it produces. Now, if we replace the verdicts by the actual state in which the monitor is after reading each of these events, we get this picture here. And you can observe that on the first event, the monitor remains in its initial state. When it reads the C, it stays in the blue state. So the pruning tactic number one is to say, let's disregard this monitor from this point on. We can just delete this instance of monitor. And the intuition is that if the monitor does not change state after reading the first event, then a stream is a match if and only if the stream without this first event is also a match. So the next event that comes in is the start of a stream that is the same match as the one that we are witnessing here. So we can discard this monitor. The second pruning tactic is to discard monitors that reach the same state at the same step. So you have example here with monitors number 2 and 4, with the portion of the trace that they read. If we draw the states of these monitors, you can observe that after the second beat in the trace, both monitors are in the yellow state. And so the pruning tactic number 2 says we can discard either of these monitors, and then we have the choice of which one we keep and which one we delete. And the intuition is that if two monitors reach the same state after reading two different portions of the trace, they will produce exactly the same verdict for what comes after. So they again represent the same match. And so we can afford discarding either of these two monitors because they will return information about the same match. Then we have pruning tactic number 3, which is the last one. We retain only what we call the progressing subsequence of the input. There's a formal definition of what this means. So for the presentation, all you need to know is that the progressing subsequence corresponds to all the loops in the state space that are removed. So in the case of monitor instance number 2 here in the slide, if you look at the sequence of states that we are after reading each event, what we will keep is only the transition between two colors. So here we will keep the transition. So for example, here, the two successive yellow states are irrelevant. We can keep just one yellow state. And so what we get here would be just one green state, one yellow state, and one red state. And the intuition is that if this sequence is a match, the progressing subsequence is the shortest subset of this stream that visits each new state in the same order. So basically, it's the essential information you need to know in order to witness that the pattern has been observed. And so now we can apply all these pruning tactics at the same time and see what is the effect on the monitors that we keep and what events we keep from these monitors. So here you have the original situation where we run one monitor for each instance, for each new event. If we apply the first pruning tactic, so let's first look at what are the states each monitor is in after reading each of these events. So if we apply the first pruning tactic, the first step tactic, you see that we only keep 3 monitor instances. Everything else is discarded. If we add on top of that the second pruning tactic, we can prune one more monitor instance because they end up in the same state at some point in the process. And then for the remaining 2 monitor instances, if we only keep the progressing subsequence of what they read, we are left with just 3 events in each of these instances. And we could argue that intuitively, this indeed corresponds to the information you need to know in order to observe that there are 2 matches in the stream, and the 2 matches are composed of the events that are highlighted here. That's the basic point of reducing information using these state-based pruning tactics. So there are pros and cons to this approach. The pros are that the pattern to look for can be any monitor. I used a very simple example, but of course we can generalize this to other monitors. It also, as you observe, drastically reduces the number of matches and the number of events retained in each match. And it produces, that's my claim, it produces results that correspond to intuition. Now, on the downside, it expects the monitor to be a state machine, and it can be seen as limiting in terms of the possible patterns that can be expressed. But we could ask ourselves the question, does it really have to be a state machine? And actually, we can generalize the notion of state, and we can extract this concept of state even for processors or for monitors that are not expressed as state machines. I won't go over this definition in detail now because we'll be lacking time. But in the chapter, we describe a way to infer the internal state of a process, even though this process is not expressed as a state machine, just by looking at its inputs and outputs. Now, the intuition is that if you have 2 instances of a process that are in the same state, it means that they have identical behavior for any future events they read from this point on. And that's the notion we generalize so that we can extract a state from arbitrary processes. We implemented these concepts by extending a stream processing library that's called BeatBeat, which is developed in our lab since 2015. It is centered on the notion that's called processor, which is a computation unit that ingests input events and produces output events. If you want to know more about BeatBeat, there's a link at the bottom of the slide where you can go look at how it works. The principle is that when you want to express complex calculations, you do that through composition. So you have elementary boxes that process streams and you connect them to each other in order to produce a more complex calculation, which creates what we call processor chains or pipelines, as you can see in the picture here. So BBEEP has been extended with a set of processors that act as monitors. So each of these boxes recognizes an elementary pattern of events. For example, something followed by something else, or two things occurring at the same time. They each provide a state function, so they can express what is their internal state at any moment, because we see that this thing is necessary in order to apply the pruning tactics that I described. And each of these boxes can also identify its progressing subsequence. So if you ask, from what you read so far, what are the events that correspond to the progressing subsequence, they can provide this information. And then complex monitors can be obtained by just freely composing these processors with everything else that's present in the BBEEP library. So here you have an example of the pipeline that corresponds to my example, where you have an A eventually followed by B, eventually followed by C. The other interesting feature is that in BBEEP, processors can define associations between output events and input events. I won't have time to explain the details of this, but there's a paper we published a couple of years ago that describes this feature that we call explainability. So in the case of monitors, we can associate the verdict produced by a monitor, which corresponds to a pattern match, to the progressing subsequence of their input, and we can propagate this information. So here you see an example where if I give an input stream to this monitor, I eventually get the true verdict at the right of the slide, and then I can retrace which events of the input are relevant to produce this true verdict. And you can see at the left that the three letters that are highlighted, the A, the B, and the C, actually correspond to the three events I need to observe to be convinced that the pattern has been observed, has been found. So here's a sample script. So you interact with the library using Java code. So here you have the complete code that produces the pipeline that you see in the screen. And if you want to detect the pattern and produce the witness, well, you use this piece of code here. So here I enter a string of characters. I push these characters into the monitor. Eventually, I get the true output, and then I ask to the pipeline, tell me what is the progressing subsequence that corresponds to this match, and it produces the output you see at the bottom. And the numbers that you see there corresponds to the position of the three events of the input that corresponds to the witness of the occurrence of my pattern. So in order to evaluate the solution, we implemented pattern monitors to detect what I call distilled or simplified versions of real-world attacks and intrusion. The first is called linear sequence. It declares a match when n successive events are observed in a particular order. It corresponds to a pattern that has been observed in the ptrace exploit that is a well-known security incident. And this is the monitor that observes this pattern. Then we have combined, that declares a match when n other patterns have been observed. One example of that is the GAN crab attack, where the attack succeeds when multiple patterns, independent patterns, are observed at the same time. So this is, again, the monitor that observes this pattern. Then we have incomplete, where we declare a match when more than n instances of a sequential pattern are incomplete. One example of that is SYN flooding, where you initiate many you start many TCP connections without going all the way to the end of the initialization of the connection. And so this is the monitor that observes this pattern. And then we have threshold, where you declare a match when more than n instances of a pattern have been observed. For example, if you have port scanning, you have a precise pattern and you observe it multiple times. And one example of an attack is the remote access Trojan. And this is the monitor that observes this pattern. And then we run this on sample traces, and we ask ourselves three questions. The first one is, do the pruning strategies indeed reduce the number of matches? And so here you have a graph that shows for each of the four patterns how many matches are observed if you don't do any pruning, and then if you successively apply each of the three pruning strategies that I described earlier. And we can graphically observe that indeed there is a reduction in the number of matches that are reported. The second question is, do the pruning strategies reduce the number of events included as witnesses? So when there's a match, does it reduce the number of things I include in my match? So here you have a graph that says that shows again the same trend, that as you apply further and further pruning strategies, you reduce the fraction of the log that you include as your witnesses. And it can go from close to 100% in some cases as to under 20%. And the last question is, what is the impact of the pruning strategies on processing time? Because of course that's an important matter. And here, of course, you observe the reverse trend in some cases, because as you apply more pruning strategies, of course, you have more processing to do, and so it takes more time. But in some cases, it can still reduce processing time, because since you delete monitor instances at some point in the trace, it means that these are monitor instances that you never have to care about for the rest of the execution. So in some cases, such as in the case of the combined pattern, you see that there is actually a reduction in processing time when you apply pruning compared to if you run one monitor instance for each input event. So to conclude, a few take-home points. The first one is that we claim that intrusion patterns or attack patterns can be formalized as runtime monitors. We have seen that stream processing pipelines can allow the expression of complex monitors representing complex patterns. We've seen that reducing the volume of data produced by pattern matches can be done using relatively simple state-based pruning strategies on these monitors. And I've shown a proof of concept implementations of these concepts in an extension of an existing stream processing library. If you want to have more information about either the library itself or the work that I presented today, I give you a few pointers to our research lab and to the Beep Beep stream processing engine. And I thank you for your attention, and I'm open for any question.
The possibility to process or to analyze different monitors in the same time. Is there a possibility to have a multi-threading in Beep Beep, or we need to write a more complex monitor?
Its own thread and analyze the same input stream in parallel to the others. So if you have independent monitors, that's fine. You can parallelize in this way. Now, parallelizing a single monitor, I did some work a couple of years ago along these lines, and it's very tricky. If you have one pipeline and you want to have multiple sections of this pipeline to run separately in different threads and then synchronize at some point downstream, it is doable, but it's extremely tricky and delicate. So the way you suggest is actually interesting, that you have independent monitors that each brings a piece of the puzzle, and then you combine the verdict of these monitors to detect a more complex attack. Is that what I understand? Yeah.
Yes.
So I didn't look into that, but that would definitely be an interesting follow-up to this approach. Yes.